Okay, you guys, so the reason we're talking about electrons, no. We know why we're talking about electrons. Electrons are super important in terms of like understanding structure and function and properties of substances. That's not what I wanted to say. What I wanted to say is the reason we're talking about light is because there is a very interesting relationship between light and electrons, and it's this. Electrons are particles that travel as waves, just like photons of light travel as waves. Now, photons of light have no mass and electrons have mass, so that's a difference between them. But this wave nature of electrons and the wave nature of light are the same thing, like they behave the same way. The other thing that's cool is that electrons have specific quantized amounts of energy, just like photons of light do. And because of that, there's this interesting play between electrons and light. Electrons are actually able to produce light, and light is actually able to eject electrons from atoms. So there's this relationship between these two things that's going to help us understand where electrons are in the atom, how much energy they have, and how they help determine the properties of a substance. Okay, so that's why we're talking about this. Let's do a quick review of light and electromagnetic radiation. When I say electromagnetic radiation, I'm referring to any energy transfer that is happening at the speed of light. Okay, so this is energy transfer or transmission. I told you my handwriting would be bad. Energy transmission in the form of a wave. Traveling at the speed of light. And if you recall, our variable for the speed of light is c, and the value, the magnitude of it, is 3 times 10 to the 8th meters per second. All electromagnetic radiation is traveling at that speed. That does not mean, however, that it all has the same amount of energy. It does not. There is high energy electromagnetic radiation and there is low energy electromagnetic radiation. And so let's take a look at this electromagnetic spectrum that you've seen a gajillion times before. Maybe you could kind of sketch it out. You don't need to write down every single type of radiation here. In fact, like all of these down here, FM, TV, shortwave, AM, those are all just types of radio waves. But what I want to remind you guys is that down here at the gamma ray end of our electromagnetic spectrum, this is high energy radiation. Right? Like we would not want to expose ourselves to gamma rays because it's such high energy radiation, this would damage the DNA of our cells and cause cancer. Down here at the low end of our spectrum, we have radio waves. This is our low energy end of our spectrum. Right? We don't worry about how much radio waves we've exposed our bodies to, right? Like we don't say, oh, turn off the car radio, we're being irradiated. It doesn't matter. It's really low energy radiation. It's not harming us. But as we go up and up and up and up and up past visible light, here is where we start to protect ourselves, right? UV, we protect ourselves from UV from the sun with, clothes and sunscreen. We protect ourselves from X-rays. When we get X-rays on certain parts of our body, we cover up the other parts with like a heavy lead vest. And of course, we wouldn't seek to expose ourselves to any form of gamma radiation. Okay. So even though all of this energy is traveling at the same speed, they do not all have the same amounts of energy. This also applies to visible light. So you guys can see here in your spectrum, so maybe sketch this out like gamma, X-ray, UV, and then pop out the vis portion. And then lower than the visible light would be your IR, your radar, and your radio. The visible light is really important to us because in the lab, we can see this with our naked eye. So like we can see when we heat up sodium, we can see the yellow light that it produces. When we heat up lithium, we can see the red light that it produces. So this is your low energy end of your visible light spectrum down here with red. That's probably around 750 nanometers, just to give you an idea of how long are these wavelengths down here. And this is the high energy end, the violet. Oops, I was writing in all caps and then I quit. Oh, what? M's only has 2 dots, not 3. All right, so this is my high energy end of our vis light. It's around 400 nanometers. It's about the limit that we can see. And if you want to remember these colors of light in order from low to high, of course, the famous Roy for red, orange, and yellow, G for our greens, B for our blues, indigos, and violets. Roy G Viv. And that's from low to high. So clearly, you guys, there's this relationship between the energy that a wave has and its wavelength that I've referred to down here. So let's remind ourselves about the variables that we can use to describe a wave. So like peak to peak distance, I've drawn this little wave over here. It's pretty ugly, I'm bad at drawing. The peak to peak distance is your wavelength, symbol lambda. Oh my God. Not you. All right, so this is wavelength. I'm not gonna go through and define everything again, you guys, you know this stuff. Peak to peak distance. The other variable that's important to us when we're measuring the energy of a wave is its frequency, or how often it repeats itself. Like this wavelength that I drew is pretty long. It's like a big long wave. Long wavelengths have very low frequencies. Frequency, the symbol is like this cursive V. This is called nu. That's the Greek letter nu. All right, but nu is the frequency of the wave. How often does it repeat itself? If I had another wave, if I drew a different wave down here, and it looked like this, this wave has a much higher frequency. Right? It's got a lot more repetitions per second. Okay, so wavelength is your peak to peak distance. Frequency is repetitions per second. So let's talk about units here. So our unit for frequency is going to be 1 over seconds to represent, however many repetitions per second. You could also write that as seconds to the -1. This is also called a hertz, Hz. Those are all the same thing. How many times does the wave do this per second? Wavelength, because we're talking in distance, obviously our SI base unit for distance is meters. But you'll notice, you guys, the visible portion of the spectrum, it makes the most sense to be talking in nanometers, okay? So typically, yes, our base unit is meters and our speed of light is meters per second, but oftentimes you're going to see your wavelengths reported in nanometers because that just sort of makes the most sense for visible light. And in fact, there's a nice little chart in your textbook. I'm going to refer to a page since you're going to go read it tonight anyway. On page 208. Page 208, table. I want you to go take a look at this table tonight. Table 6.1 refers to the different units that you would use depending on which part of the electromagnetic spectrum you're talking about. Like it might make more sense when you're talking about X-rays to be measuring in something called an angstrom, which is a power of 10 off from a nanometer. So go look at those different units and familiarize yourself. Okay, wavelength and frequency, done and done. What do you guys notice about the relationship. I realize I'm asking questions and I've got 23 of you on Zoom, so maybe this is not the best format. Just think about it. What do you guys notice about the relationship between wavelength and frequency? Like when I've got this big, long wavelength, low frequency. Short wavelength, right? So like we look here at these little short wavelengths and we get a much higher frequency. Oh yes, inversely proportional. Perfect, good idea you guys to hit me up in the chat when I'm recording. Yes, excellent. So this is an inversely proportional relationship. So when one thing goes up, the other thing goes down. And if that's the case, when you multiply wavelength times the frequency, you're always going to get the same number, because if one of them is going up, the other one's going down. And so the product of those two values is a constant. That constant is the speed of light. I'm going to write my equations up here because I didn't quite leave myself enough room. Okay, so here are my light equations. C is equal to lambda mu. That is one of my equations, right? And obviously my speed of light is 3 times 10 to the 8 meters per second. And the reason why this equation is the case is because wavelength and frequency are inversely proportional. You know, I think my handwriting's a lot better when I'm up the top of the screen, because my whole hand can sit on the tablet. I think I just figured that out. I need to say hi on my screen. Okay. You may remember the second equation that relates the frequency to the energy of a wave, right? So if I'm looking here back at my electromagnetic spectrum, I can see here my higher energy radiation has shorter wavelengths and thus higher frequencies. So when we have a high frequency, we have high energy. Those things are directly proportional. And so my equation looks like this. Of course, I'm going to need a constant to relate the proportionality between those things. E equals h nu. That constant was the guy who came up with this relationship, Planck. This is Planck's constant. Relating the energy and the frequency of a wave, it is 6.626 times 10 to the negative 34 joules times seconds. And that makes sense, right? Because if my frequency is in 1/seconds, I multiply that times Planck's constant, and I'll get however many joules of energy that light has. So if I was to look at my units up here, my wavelength needs to be in meters, my frequency needs to be in 1/seconds, and then I'll get my meters per second for my speed of light. So the only thing you have to be careful of when you're using these two equations, you guys, are your units, right? Make sure your wavelength units are in the appropriate unit. Yeah.
Is your exponent on Planck's constant 39 or 34?
Oh, sorry, it's 34.
Thank you.
Okay. Yeah, there's a little squiggly there that kind of looks like a 9. Okay, so energy and frequency are directly proportional. And I just remember that, right? Because like if you think about a high frequency wave, I don't know, in my mind, it's like, it looks kind of crazy. You know, it's got like all those repetitions per second like that. So obviously it makes sense that that would be a high energy wave. I mean, they're all traveling at the same speed, so maybe my analogy doesn't work for you, but that's how I remember it. Okay, let's do a quick little practice problem. What is the frequency? So calculate frequency first, and then calculate energy of a photon with a wavelength of 589 nanometers. So So you're going to need to do your nanometer to meter conversion, and then go into your speed of light equation, and then go into your energy equation. I'm going to pause the recording for a sec. Okay, and for those of you that need a little assistance with your unit conversions, remember this thing? Giga, mega, kilo, base unit, deci, centi, milli, micro, running out of room, nano, pico. So here's our base, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 times 10 to the 9th nanometers in a meter. So everything over here to the right is a smaller unit than the base unit. Everything here to the left is a bigger unit than the base unit. You can just see kilo is 1, 2, 3 units away from the base, or 3 times the base, power of 10. Ugh, I'm talking all crazy. You know what I mean, 1,000, 3 zeros. All right, go ahead, you guys calculate. Don't look at my work, do it yourself. I'm gonna go slow. Hopefully you're ahead of me by now. All right, hopefully you guys got around 5.09 times 10 to the 14th hertz for your frequency. And then you're going to go into your energy equation. Remember to use that EE button on your calculator. Don't do times 10 to the caret. Don't do all that nonsense.
Mr. Vera, would it be? Maybe I did something wrong. Okay, actually, no, maybe I did. I got 15 for the exponent. I got 10 to the 15th, not 10 to the 14th. Wait.
Oh, hang on. Did I do something
No,
wrong?
I think actually, wait, because it's. Did I do it? I'm not sure if I did it wrong or not.
So 3 times 10 to the 8th divided by 5.89 to the negative 7. No, I'm right, Eddie. I don't know what you're doing. Are you using that E button on your calculator?
No, I realized what I did. I just
Okay.
carried down the 5.89 instead of like added the exponents.
Okay.
What's the H to Z?
Hertz. It's another unit for frequency. It's the same thing as 1 over second. All right, and so for my energy, I got 3.37 times 10 to the negative 19 joules. That's a teeny tiny amount of energy, right? You guys, I mean, think about the heats of reaction and stuff that we were working with. Those were like kilojoules and stuff. Those were huge amounts of energy. The reason why this number is so teeny tiny, and this is something new that we didn't discuss last year, Planck's constant, you guys, was developed off of the energy associated with one photon. Just one tiny, think about how teeny tiny a little packet of energy a photon is. So of course, this amount of energy is super duper small, okay? So technically this number is joules per photon. It's per one photon. In other words, if I then went on to ask you how much total energy would you get if a mole of photons were released, like, in fact, let's just add this to the problem because the AP exam loves this question for whatever reason. They just love Avogadro's number. Let's say the question then said, how much total energy would be transmitted by 1 mole of photons with this wavelength. All you would have to do, you guys, is multiply by Avogadro's number, right? So here's your dimensional analysis. 1 mole of photons. You know that 1 mole of anything, 1 mole of photons, contains 6.02 times 10 to the 23rd photons times the amount of energy we get, 3.37 times 10 to the negative 19th joules. This many joules per 1 photon. Okay, so if it's ever asking you, 1 photon versus a mole of photons, don't forget that you know Avogadro's number, right? So there your moles of photons cancel, your individual photons cancel, and this is the total amount of energy you would get. And you'll see it's a much more reasonable number that's kind of on par with the types of energy transmissions we were seeing in our thermo unit. So 203,167 joules. Let's take that to kilojoules and go with 3 sig figs. Okay? Any questions there? So I would expect you guys to be able to do any sort of, E equals H nu, C lambda nu type problem with unit conversions embedded in them. Easy stuff. Okay. So now that we know how we can measure wavelength, frequency, and energy of light, now we can start talking about that relationship between light and electrons, which is the cool part. There we go. There were 2, count them 1, 2, sort of interesting phenomena that scientists noticed that led to this quantum model of the atom. The first was the photoelectric effect. And this was noticed by Einstein. I don't think we talked about this last year, so we'll talk about it now. Einstein observed that when certain frequencies of light were shown onto a metal, electrons were emitted or ejected. Off of it. Just kind of interesting, right? So like you shine a certain frequency of light onto that metal substance, and electrons would actually be ejected or emitted from that substance. And you can actually measure the speed at which those electrons are coming off. We're going to actually use this to identify unknown substances a little bit later on in the unit. But what was really cool about the photoelectric effect is like it had to be a certain frequency of light. If the frequency was too high or too low, the electrons were not emitted. And the frequency depended on the identity of the element. So like different metals require different frequencies in order to eject their electrons. So if we think about like, well, what does that mean? Like, why is that the case? It must be that electrons have a certain amount of energy, potential energy, keeping them attracted to that nucleus, right? You've got positive protons in the nucleus, you've got those negative electrons on the outside. There's a measurable amount of potential energy holding those electrons in place. And if you give it just the right amount of energy, you can eject that electron. The fact that every element is different must mean that the electrons in one atom are in a specific unique place as compared to another element. So they're starting to formulate this idea that electrons exist in certain specific places with certain specific amounts of energy, depending on the identity of the element. This was further, sort of verified by Bohr's observation of atomic emission spectra. And you guys saw this last year. Bohr observed that when elements were heated, a little squishy, were heated or electrified, they emitted unique colors of light. When you look at that light that the elements are emitting through something called a spectroscope, which separates the colors into all of their individual components, you'll see very specific wavelengths of light being emitted. And they are different for every element. It's like a fingerprint. So to the naked eye, it would all appear as like one color. So like when we do this in the lab, when I electrify hydrogen, it's gonna appear mostly purple to the naked eye. And that makes sense, right? Because look at all of these purple wavelengths that hydrogen can emit. And when we take sodium and we put it in the Bunsen burner flame, it's gonna seem mostly yellow to us because here we go, we've got all of these yellow, its two most prominent lines are yellow lines. But if you look at it through a spectroscope, which we will also do, you'll actually see those colors separated. So we need a model that can explain what's going on here, right? Like clearly there was this idea or a conclusion drawn from these two key observations. And the conclusion was this: electrons must have quantized amounts of energy. A quanta is just a specific amount. It's like a set or a certain amount. And the model that Bohr developed in order to explain how much energy these electrons have and how they can transmit these quantized amounts of energy is called the Bohr model of the atom. And I have one over here to the right. Go ahead and sketch a Bohr model for yourself. Okay, so here's the gist of the Bohr model. Obviously, we've got the nucleus down in here with our protons and are neutrons. And what Bohr said is like, okay, if these electrons have to have certain amounts of energy, let's, in our mind, place them in these set circular orbits of increasing energy from closest to the nucleus to farther out from the nucleus. These are called principal energy levels. So n equals 1, 2, 3, et cetera, up to 7. These are called our principal energy levels. And these are discrete places where the electrons can exist. These orbits are discrete, meaning they are unique in terms of how much energy each one has. Discrete, set, circular orbits. And the ones closest to the nucleus are your lowest energy, and the ones farther from the nucleus are your higher energy. And this is where the electrons exist. So like, let's say I have an electron here in the n equals 1 energy level. If I were to heat or electrify this electron and give the atom energy, this electron can move up away from the nucleus because right now it's attracted, positives to negatives attract. But if you give it enough energy, you can actually get it to move up into a higher energy level. So let's say it moved up to like n equals 3. Out here, the electron is unstable, right? Because it's attracted to those protons in the nucleus. So eventually, that electron is going to fall back down. It could fall down to n2, it could fall all the way back down to n1. However far it falls determines how much energy is emitted, right? Because if it absorbs this much energy, it has to release energy in order to come back down. And so that energy is emitted as a photon of light. You can see here on this diagram that I picked, this showed a transition from n equals 2 down to n equals 1. I showed you a transition from n equals 3 to n equals 1. The bigger your energy transmission, or transition, sorry, the bigger the energy transition, the more energy is emitted. Okay, so like this transition was much bigger than this one. So I would expect this photon to have much more energy than this photon. So if like this photon that was emitted down here was blue. Thank you. I would expect this transition to be a higher energy light than blue light. Maybe it's a purple photon. Maybe it's violet. Purple photon. Sometimes, you guys, these energy transmissions are so big that it doesn't even fall in the visible light portion of the spectrum at all. It's quite possible, in fact, that the energy transitions land us, back to my electromagnetic spectrum, land us in the UV range. Like there are some transmissions that are so high energy that you can't see them. There are also some that are really low energy, like infrared. So it's possible that in the lab, yes, we're going to see energy transitions that result in visible light, but it is also possible, many atoms in fact have transitions that are outside of that visible spectrum, that are UV or IR. In fact, hydrogen has a couple, I think it's called like the Lyman series. They have like special names when they fall outside of the visible spectrum. I don't remember exactly what they're called. It's not important. But somebody did ask that question today. They were like, well, what if the energy transition was like greater than something that would emit violet light? What happens? Well, it's still there. It's still an energy transmission. You just can't see it. Okay. So this is how the Bohr model explains what's going on with those atomic emission spectra. And the reason why the spectra are unique, right? Like the reason why hydrogen is different than helium is because every atom's structure, like everybody's N1 is not the same. All atoms N2 is not the same distance away from N1. Like where these energy levels are and how much energy they have is unique to every atom, okay? So if we want to answer the question, oops, sorry, I'm still using my phone. If we want to answer the question, why are spectra unique? It is because every atom has a unique number of protons, and thus the energy levels are at different distances from the nucleus. Think about it like radius. It is radius, essentially. Every atom has a unique radius. And those layers of electrons between the nucleus and those outermost electrons, all of those layers of energy levels fall in certain places for certain atoms. So like if we look up here again at some of these examples here, these are the only 3 colors of light that sodium is able to produce. It is not able to produce a transition that could give you purple light because those energy levels, those distances between the energy levels just don't exist in a sodium atom, but they do in a helium atom. So these electrons can only be located in these set quantized places, right? Certain amounts of energy.
What's the PT when it says like every atom has
Number, oh, it's sorry, it's protons. That's
Okay.
supposed to be a plus sign. Okay. There's another equation we can learn. I think I did this with some classes and didn't do it with other classes. If you were in honors, you probably did this equation. If you were in CP, you might not have. It's called the Rydberg equation. And it's not hard, it's just kind of annoying. The Rydberg equation. What the Rydberg equation allows us to do is it allows us to calculate the wavelength of these photons just by knowing the energy levels that the electron transitions between. Okay, so like if I don't know the wavelength of, if I don't know what color this light is, I don't know its wavelength, if I just wanted to predict it, I could do so just by knowing that the electron fell from N2 to N1. So here's the equation. Slow me down if I'm going too fast, you guys. I'm not looking at you, so I don't know. We're okay or not. 1 over lambda, okay, so we're going to be able to calculate the wavelength, is equal to Rydberg's constant, this is the constant, times 1 over the energy level of the lower orbit squared minus 1 over the energy level of the higher orbit squared. I think I gave you Rydberg's constant in centimeters last year. I'll give it to you in meters this year, because I think that's what they give it to you in your book as. 1.1 times 10 to the, see, I have it memorized. 1 times 10 to the 7th. Meters to the -1, or over meters. That's just the unit for this constant. And the reason why it's meters to the -1 is because you can see here our wavelength is in the denominator. So when we go to do all of our algebra, we're going to need that to be able to be an inverse. Okay, so let's calculate what the wavelength would be for a transition from, let's say, N3 to N2. Okay, so the question is, what is the wavelength of light emitted when an electron goes from n equals 3 to n equals 2. All right, do good algebra, people. Don't watch me. Do it yourself. I know you can. Okay, Samantha, just make sure you get the rest of the notes from somebody. Oh, I'm recording it, so I'll post the video tonight.
Yeah, that's because you said you were recording.
Yeah.
All right.
So you can just go watch the rest of the recording later.
Okay. Thank
Okay. Yep. Bye.
you.
Ms. Rivera,
Yeah.
so how can this equation be the same for like all different like elements or whatever? If they said like the energy levels are different, is it like some don't have certain energy levels, like it skips from like 1 to 3, or like the radius is different? Like how can it be the same? Is it just proportional?
Isabella, you are too smart for your own good. This equation falls apart after hydrogen. It only works for hydrogen. But I don't like to tell people that because they're like, then why are we doing this big annoying equation?
Okay.
So you ruined my strategy
Sorry.
because you were thinking. Yes, so Isabella was thinking, and she's like, how can we use this equation for every atom if like we should be getting different colors of light when it transitions from 3 to 2? Yes, Isabella, that just like made my whole day. When students are thinking deeply, that makes me so happy. I'm sure some of the rest of you guys are thinking that too. Yes, it only works for hydrogen. The reason why we're doing it is because I like to torture you with algebra. And because like I want you to have a little empathy for Bohr, who like does all of this work, comes up with this amazing model that totally works for hydrogen. But the model's not all bad. Okay, so we'll talk about that when we're done doing our algebra. That was amazing, Isabella. Yay. All right, 1/4 minus 1/9. And then just go ahead and get out of the fractions, you guys. Work in decimals here. So 0.139. All right. Times. Okay, so I'm at 1 over lambda equals meters to the -1. And so to solve for lambda, I'm going to need to take the inverse of this. So lambda will equal 1 divided by that. And I get a much more reasonable number. I get 6.55 times 10 to the -7 meters. Let's turn it into nanometers to see if it makes sense. 1 meter is 1 times 10 to the 9th nanometers. So that would be what, 655? That would be visible light. Yeah, so that makes sense based on that diagram I gave you guys, right? That we would see a transition from 3 to 2 with visible light. Now, like Isabella said, this only works for hydrogen. So sad, too bad. Only works for hydrogen. So there were some limits to the Bohr model, you guys. We will talk about those limits and then we will be done. Where should I talk about them? Over here? Sure. Limits of the Bohr model. Limit number 1 is like we just said. It only works mathematically for hydrogen. It works conceptually for everything, right? Like this idea that electrons have a set amount of quantized energy and it can go up in energy level and down in energy level and emit light, that still works, okay? It's just the math, this Rydberg math, that falls apart. Here's the other thing. It can't explain bonding, specifically covalent bonding. Like there's no way for us to explain all of those interesting geometric shapes. Remember, like tetrahedral and square planar and trigonal planar and bent. Like we can't explain all of these shapes in covalent bonding with these like two-dimensional set circular orbits. Like that doesn't make sense. So we're going to need a better model to help us explain bonding. And then lastly, turns out that electrons don't move in set circular orbits. A guy by the name of Heisenberg kind of blew up Bohr's model by telling Bohr, actually, you don't know where the electrons are at all for certain. You can only base your electron location on mathematical probability of where we think the electrons are. So we'll talk more about that in tomorrow's lecture, for those of you that are doing the lecture tomorrow. Some of you guys are going to be doing the lab here in class. Okay, so like why do we still hold on to the Bohr model? Why is it still being taught to you guys in middle school and in high school and in college chemistry? It's because this idea of electrons having quantized amounts of energy and energy levels is still good, okay? So, oh, no. Okay, there we go. This idea that electrons in energy levels and able to transition between them and emit light still makes sense. Right? This is true. Energy levels, transitions, and their relationship to light, all facts. Now, where those electrons are located, not in these set circular orbits, we will further develop with the quantum mechanical model tomorrow. And I think that's all I wanted to talk about, and my timing was impeccable.